Okay, guys, it's 9 o'clock. A lot of stuff to cover today. Let's go ahead and get started. I'm going to cover 2 PowerPoint presentations today on Chapter 7 and Chapter 8. So let's get going, and I'll start sharing those now. Okay. Share files. Share this one. Share now. Okay, wide area network concepts. And as we remember from our fundamentals class, we talked about local area networks and wide area networks. Local area networks where that would be within the building, within the home, within the enterprise. So we were limited by the wiring capabilities of the wiring within the home or the wiring within the business. So we're limited to the Wi-Fi range, or limited to 300 feet that Ethernet can go. Or, for example, in the case of South Campus, we can link the buildings together with fiber optic cables. So it was very high rate of speed, permanent 24-hour day connection, and it was controlled by us. We got to choose what type of technology we use. Wide area networks, on the other hand, Tarrant County College did not have the right to dig a ditch between South Campus and Northeast Campus and Northwest Campus and run on wires. We have to lease those wires. We have to rent those wires from the common carriers, like the phone companies and the cable companies, that have the rights to lay those cables. So the classical definition of wide area networks was something to connect together local area networks that were in different offices in different cities, usually at a lower rate of speed, although the speeds have gotten much faster these days. So for example, in the 90s, when I worked for Harcourt, we had standard Ethernet in the office, and we had T1 lines connecting our offices together at very slow speeds. T1 can go for a megabit and a half, but we had fractional megabit. So these days the WANs have gotten much faster. Our classroom is a gigabit Ethernet, Ethernet wire attached desktop computers, and we use 10 gigabit Ethernet over fiber optic cable between the buildings and over the connections we lease from the phone company to go back to all the other offices, all the other campuses. So in a data center, it's maybe a different story. In a data center, you're probably using 25 gig or 40 gig or 100 gig connections between all your massive servers. But all your people that are logging into those servers, everybody's working at home now. So what's the best we got at home? You guys on cable are maybe 200, 300 megabit. I'm on telephone company, about 75 megabit. But the cable and telephone companies are generally starting to offer fiber optic connected services, and they're generally in the gigabit range. Okay, so we'll look at some wide area networks. I already started talking about that, how they operate, traditional and modern, and then internet-based connectivity purposes. So local area networks, small geographic area, stuff within the building, stuff within the home, or owned by the organization or a home user. There's no cost for using this. You just have to buy your home router and plug everything together and Wi-Fi everything together. And wide area networks there's a charge. You have to pay a monthly recurring charge based upon, is it fiber optic, is it twisted pair cable, what are the speeds that are involved. But we don't have the right to run our own WAN services. With some slight exceptions, there are some point-to-point radio connections that you can get and sort of bypass the phone company, but you can't run from LA to New York with that. So we can lease a circuit from the phone company or from some carrier over large geographical areas. So a private WAN, as this contrasts this with the public internet. So the legacy was we would lease a T1 line between the Fort Worth office and the Orlando office. We would get a T1 line, twisted pair cable, dedicated wire that ran all the way between the 2 locations. And this would give us, since it's our own wires, and no one else could use it, we had some privacy and some security. I'm just checking attendance. 1, 2, 3, 4, 5. Okay. As a contrast to a public WAN connection, that typically goes to the internet. So the financial guys started asking, why do you need a private connection to the offices and a public connection to the internet too? So later on today we'll look at this issue of, well, if I have an internet connection anyway, why can't I use that for my office-to-office connections? Well, everybody can see your data, but we can use a virtual private network and encrypt that data so the competition can't see it. Okay, so let's look at some topologies here. Point-to-point topology is a point-to-point circuit. So for example, there was a physical wire running between the Fort Worth office downtown and the Orlando office right across the street from SeaWorld. So it's a layer 2 transport service. The phone company had a proprietary method of encapsulating your frames and sending them back and forth. So we can think of it like Ethernet, except its frame is not exactly Ethernet connection. It's kind of similar to Ethernet. It has source and destination addresses. It has a frame check sequence like a CRC. It is expensive, and it can become more expensive if you use many point-to-point connections. So if I used, this would be an example of the hub is the home office in Orlando, and spoke A and spoke B and spoke C are the office in Fort Worth, and the warehouse in Irving, and the shipping warehouse up in Michigan. This problem is, since all of the spokes run back to the hub, if the power failed in Fort Worth, or I'm sorry, if the hub is in Orlando, if the power failed in Orlando, we lose connectivity between the branch offices because everything is routing back through that hub connection, hub and spoke type connection. So some technologies were developed like frame relay that allowed more like a mesh type connection, where there was if the hub in the Orlando office failed, the Fort Worth office and the Irving office could still talk to each other because they had their own different connections. Okay, there's a downside in that it's more expensive. We have to pay for extra virtual circuits or extra actual real wired circuits to go back and forth between these places. So in a fully meshed technology, the carriers love this because you're paying for lots of circuits, but it is the most fault tolerant. So when you think of fault tolerant, think of like a RAID driver RAID. One of the drives can fail and you can still don't lose any of your data. So fault tolerance with the wiring is any one of these wires could get dug up or could fail, and we could use an alternate method of communicating between the branch office locations. That's pretty expensive, so a slightly cheaper method at the bottom is a partially meshed topology. So the home office would connect to all 3 branch offices, and maybe there's an extra connection between some of the more important branch offices. And that sales office in Topeka or something that there's many people in it, he just gets the one connection. So when we look at these carrier connections, how do we connect to the internet? We usually go to a service provider. And now when you get your cable modem connection, that is best effort. There is no service level agreement. So if you lose your cable, if your cable goes out, they're not going to refund your whole thing you had to pay for the whole month. They might give you, 1-day credit. A service level agreement, they actually guarantee to provide, 99% or 99.999% all the time. And if they fail to maintain that, they have to pay big penalties for this. Because in business, we lose revenues if the line goes down. Think of Amazon. If they lost their connection, they're losing millions of dollars every second that service is down. So if we use a single carrier, we negotiate a service level agreement between that particular service provider. Now, what if it's AT&T and AT&T goes down and we don't have a backup connection? So some companies will use 2 different carriers. They'll use 2 connections to get to the internet. Don't have both of them AT&T. If AT&T system goes down, you still have no connection. Maybe use Verizon for one and use AT&T for the other, or something like that, where if one carrier goes down, maybe the other carrier is still working properly. So that way we at least have a backup connection that we can still connect our customers' can come from the internet and still talk to us, even if one connection goes down. Okay, let's look at WAN operation and look at some of the organizations that have put together some standards for here. The Telecommunication Industry Association, Electronic Industry Association, are a group of people that are advocates for selling equipment. They're composed of the manufacturers and the vendors that make the equipment, and it's in their best interest for people to buy a lot of equipment from them. And if the equipment all interoperates with each other properly, they can sell more equipment. So like in the old days of computers, if you bought an IBM mainframe, you had to buy IBM terminals. You couldn't buy another brand. Eventually we got the OSI 7-layer model, and we got some interoperability between different vendors. So the ISO is the standardization organization that does many things, not just communications. For example, the ISO has standards for a number 8 screw. How many threads per inch is that? So you can buy screws and nuts and bolts from any company, and they'll all fit with the others. And it's the source of our dreaded, feared, and hated OSI 7-layer reference model. The IEEE is the Institute of Graduates of Engineering Schools who are electrical and electronic engineers, and they've written from standards, so for example, the 802.3 standard for Ethernet, or the 802.11 standard for Wi-Fi. So here's my argument I'm going to make for you guys here is WAN protocols and LAN protocols all exist at layer 1 and layer 2 of the OSI layer model. I can think of one exception only. So when you think of Ethernet, Ethernet is a physical and data link layer technology. We normally call it a data link layer technology because its sophistication rises to the level of the data link layer. It has physical layer stuff like the RJ45 connectors and the bits of electricity, the ones and zeros that shoot out into the electrical wires. But it mainly rises to the data link layer sophistication. It has frames that can't be too big and too small. It has a frame check sequence to check for errors. It has a access to media thing that says you're not supposed to transmit your Ethernet frame unless the wire is quiet, or otherwise you'll get collisions. And it has this MAC address thing so that we can, instead of being an anonymous series of bits at the physical layer, you have an identity at the data link layer. You have a MAC address. Later on, I'll map that MAC address to your IP version 4 or IP version 6 address. So at level 1, we can use lots of different technologies. We can use fiber optics, different technologies to get higher speeds. At layer 2, we can use wireless. We can use Ethernet WAN, like Metropolitan Ethernet. Point-to-point protocol was a protocol that was developed to overcome the old standard for Cisco serial ports, used HDLC, but it was Cisco to Cisco only. So point-to-point protocol was developed so that any one modem or any one serial port could talk to any other serial port. Remember the old days of America Online? They were modems. There were 10,000 different modem manufacturers and models out there, but they all interoperated with each other because they all use point-to-point protocol to send stuff back and forth. Frame relay was a technology that was very popular in the 90s as a cheaper alternative to dedicated at least T1 lines. And another darling technology of the 90s was asynchronous transfer mode, which was overpriced itself right out of the market. It was much more expensive. It was much more expensive than standby one. It was much more expensive than standard Ethernet, or it was even more expensive than token ring technology. But some big carrier companies and big media companies adopted it. The telephone company still uses it to backhaul. If you have the old legacy DSL service, I used to have that. They use ATM to backhaul it, but it would cost you about 25% of your bandwidth because they had to take all those large Ethernet packets and put them in the teeny-weeny ATM cells and re-encapsulate them back and forth. Okay, DTEs and DCEs. And let's make this, think about the 1990s when you or your parents had a dial-up modem and they would dial into America Online, or they would dial into the bulletin board system, or they would dial into the Star Telegram Star Text service. or at the beginning of the days of the internet in the early 90s, they would dial into an internet service provider. So what's this DTE, DCE stuff? So data terminal equipment, it would be the computer. It starts the flow of data and it receives the answer back. The DCE is the dial-up modem. It would convert the digital ones and zeros from the computer into the analog screeching cat's noise that would go over the modem and go over the phone lines, because they weren't designed to carry digital. Dial-up phone lines can only carry voices and noises that you can hear. So the DTE today is your home home computer, all your home computers. The DCE is your cable modem or your DSL modem. It converts your Ethernet signals from your home into a signal that can be sent over the cable wires or over the telephone company wires back to the internet. Customer premise equipment is the equipment that you own. Now, back in the days, in the early 1980s, we had something called divestiture. They took the big telephone company and they chopped it up into different telephone companies. The long distance service was run by one company. The local service was run by another company. Before that time, the telephone company owned all the equipment. They owned the phone. They owned the wires. They would maintain all the wires in your home if you had a problem with it. After divestiture, that was separated out. So now you get to own your own telephone or your own modems or your own data communication devices to plug into the network, and you're responsible for those. The telephone company's responsibility ends at the demarcation point. In your backyard, there's a little gray box about the size of a dictionary screwed to the wall, and the phone wire comes down from the pole and attaches to it. If you open up the top part of that box, you'll see a little pigtail connector that if you unplug that, it will disconnect your home wiring from the telephone company. That's the demarcation point. If your telephone stops working in the house, what you can do is go out to the box, open the door, unplug that pigtail, and plug in a known good working telephone. If your telephone works, the telephone company is not at fault. It's a problem with your inside wiring. If it doesn't work, then you can go to a friend's house or use your cell phone and call them and request service. There's also a little relay in that box that if you report a problem with your telephone service, they can send a signal out down the pole, down the wire to your house to that gray box. And if they can get that relay to click and send back a loopback signal, they have proven that their system is good. And then they'll tell you that you have to have your inside wiring fixed, or you can pay them to come out and do it. Okay, the point of presence inside a commercial building. Most commercial buildings have a place down in the basement where there's a big piece of plywood screwed to the wall, and that's where the fiber optics and the wires come in from all the telephone companies and all the service providers. And then if you're a tenant in that building, you can run a piece of fiber optic cable down to that point of presence in the building, and it's like the demarcation point. That's where you can connect to that carrier that you've chosen and get your business service that you need. The local loop is that 100-year-old piece of telephone wire that's been chewed on by squirrels and is the worst possible bandwidth, but it's the last mile that goes to the subscriber. So the DSL service that became very popular in the mid-90s and so forth could use this standard wire. It didn't need fiber optic cable. It didn't need special shield. It's typically the worst bandwidth of all because the carriers have super fast fiber optic cables and very fast speeds within their systems. The CO is a central office. That's the telephone company's central office that's closest to you that would give you DSL service or the very high bit rate DSL service like I've got, 75 megabit service. The toll network is all of the wiring and equipment that the phone companies have that go between them, or that the cable companies have that connect between them back and forth, and they can backhaul their traffic. When you do a long distance telephone call from Dallas to Chicago, it'll go over their toll network and they'll backhaul it over the best available connection to get up to Chicago. So this is the backbone of their network that they use to provide the services so they can charge you, the subscriber, for that stuff. Okay, a voice band modem, dial-up modem. This is very legacy. The Hayes type dial-up modems that were limited in speeds to about 50 kilobit per second. because the voice lines weren't capable of carrying any higher data rates than that. So still available in parts of the world where you can't get high broadband service, you can still use a dial-up modem. The DSL and cable modems are what are typically used these days. I don't like calling them modems because when you think of the word modem, it says modulator, demodulator. So it's supposed, the typical analog modems, like the dial-up Hayes modems, would take the analog, would take the digital signal from your PC and change it to the analog screeching cat's noise. And then the receiving modem would change the screeching cat's noise back to digital ones and zeros. So it actually modulated and demodulated. And it had flashing lights on it. So they still call cable modems and DSL modems modems. They still have flashing lights on them. But they're actually not demodulators and modulators. It's all digital. The digital Ethernet comes from your home network. And it's converted into, it's still bits. It never goes to the analog domain back and forth. But they always call them modems, so that's what we'll call them. If you had a T1 line or a frame relay line or a fractional T1 line like I had downtown, we would need a channel service unit, data service unit from the phone company to convert our IBM mainframe bits into the T1 frames that go over the telephone company network. So in the old days, these were owned by the phone company. These days, like you could own your own phone, you could own your own DSU/CSU device. And Cisco routers, where we have our serial port plugged into them, you can plug in a DSU/CSU converter the size of a playing card into that and have fewer wires to worry about. The 24-port switches that we have, the 2960 switches, have got 24 fast Ethernet ports and 2 gigabit ports that are RJ45 copper. And as an option, they have 2 slots. By those 2 gigabit ports, you can plug in a transceiver, and it will convert the electrical into optical pulses. So if you wanted to use a fiber optic cable between buildings because it was more than 300 feet, instead of the gigabit Ethernet RJ45 copper cable, you could plug those in and use that instead. Okay, a wireless router access point. Your home router does this. Your home router is a combination of an access point and a 4-port switch and a firewall and a Wi-Fi access point all in one. In the business world, we separate those devices out. So in the business building at South Campus, we have an access point, a Wi-Fi access point in the ceiling, and then it's connected back to a switch in the closet. It doesn't have its own switch. It doesn't have its own firewall. That's done in other parts of the system. WAN core devices are the core switches that connect our buildings, different buildings together, and they typically are very expensive. Not $500 for a 24-port Cisco switch like we have in the Cisco lab, but probably more like $50 to $1 million for very powerful, high processing capability devices that we would use. For example, we have $1 million Cisco 6500 switches, several on the South Campus. So let's look at serial communication. In the old days, in the 1900s, this is still 20th century, we would have printers would plug into a parallel port on our PC. And the printed document would be sent to the printer 8 bits at a time. Every 8 bits represented 1 character to be printed on the printer. Parallel printers have pretty much gone these days. Parallel printers, the printers are now USB attached, and USB is the type of serial communication. So in serial communication, we send each of the bits 1 by 1. Send the 8 bits 1 at a time over the serial connection. So the problem with the old parallel cables is you couldn't run the wires very long because the bits would get out of sync with each other as they went along the 8 wires. You were limited pretty much to 15 to 25 feet. But with serial communication, we can run much longer distances. We can run hundreds of feet, and since the bits are all obedient lined up behind each other, and they have a line leader, the bits don't get mixed up with each other. So that's the technique we normally use today. When you make a telephone call, that's a circuit switch communication. You pick up the phone, you dial a number, and a little circuit is stitched together with relays or transistors, and the person's phone rings that you're calling, and you have your conversation, and then we guys both hang up the phone. The circuit elements are released, and they can be used for somebody else. So the communication takes the exact same path, the arbitrary path that happened to be connected together at the moment that you dial the phone. So public switch telephone network, integrated services digital network, ISDN are examples of what the circuit is. It's predestined, like the Presbyterians. It's made it once and it's kept for the whole time. In a packet switch communication, all the circuits are active at the same time. When you send your first packet, it may take one path. When you send your second packet, it may take another path to go back and forth between the server and the client. It really doesn't matter if they happen to be received out of order, because Mr. TCP will take the sequence and acknowledgement numbers and it'll put everything back in the proper order again. So packet switch is your internet connection is packet switch now. And we can run everything over the IP packets. We can run voice over IP telephone, video, audio, data, can all be run over that. So common technologies you list here is Ethernet WAN, like Metropolitan Ethernet, sometimes called a carrier Ethernet. Multi-protocol label switching is a technique similar to the old frame relay that would set up a virtual circuit between branch offices. And asynchronous transfer mode is the technology of the 90s that's only being used now by the big carriers like the phone company. Okay, synchronous digital hierarchy, a standard for transporting data over fiber optic cable. So this is something that all the phone companies over the world use. They used to use copper cables with T1s. A T1 line would carry 24 voice conversations. So this standard was set up so that if you're calling somebody in Italy or Russia or something like that, they use the same technical standards and the phone call can be completed. And we can still share, the 600 voice simultaneous telephone calls we can have over one strand of fiber optic cable. SONET standard is a North American standard that does the same sort of a thing. So since fiber optic cables can run very long distances without having to lose data, the more expensive single mode fiber optic cables use real lasers. The cheaper multi-mode fiber optic cables you would use within your company, within your campus, only can run a couple miles, but that's all we need. And they use cheaper light emitting diodes. And light emitting diode only costs a nickel. Dense wave division multiplexing imagine if the red light on the traffic light flashed and gave one stream of data, and the yellow light flashed and gave a second communication, and the green light flashed and carried a third conversation back and forth. They can use multiple different colors that are in the fiber optic cable to send multiple conversations at the same time. So that's why you keep reading news reports of somebody did an awesome new rate of speed of transfer of data from one place to another place using fiber optic cable. Okay, in the traditional connectivity, let's look at us old network boys remember back in the 1980s. Tarrant County College was just starting to experiment with what type of connectivity should we use within the buildings. So we looked at Ethernet, we looked at token ring, we looked at a bunch of different technologies. Eventually we settled on Ethernet like the rest of the world did because it was the most practical and least inexpensive kind. So they also wanted to connect to the different offices, the different branch offices. So we typically would use like a dedicated T1 line. We would go to Southwestern Bell and order a lease line between the South Campus and the Northeast Campus where our mainframe computer was located at. So our connectivity options are, we can use a dedicated line, like a lease line, or we can use a switch technology, like a dial-up screeching CATS analog modem, or a ISDN digital modem to connect between our different locations. This is very legacy, very old. So we could lease the lines from a service provider, typically a telephone company, and they were available in different speeds, different prices. T1 lines were priced on the bandwidth required. It was up to 1.54 megabit. And you could get it at slower speeds. When I was at Harcourt in downtown Fort Worth, we had 256, we had fractional T1. And the other pricing was how many miles is it from one point to the other point, because the phone company had to dedicate and sacrifice these wires for you to use and nobody else could share them. So in North America, the T-carrier system, T1 lines were 1.54 megabits, and the fastest you could get over copper at the time was about 45 megabits using T3 lines. In Europe, they're called E-carrier instead of T-carrier, and they have a slightly higher capacity. They have like 30 channels instead of 24 channels. So point-to-point communication is if you have the wire available and it has the amount of bandwidth that you need. And back in the 1900s, 1990s, T1 was the golden standard. That was very fast. So it's plenty fast for e-commerce type stuff. Voice over IP is fast enough. Video over IP, we're starting to get kind of slow for that. However, they were kind of expensive. So it was a monthly recurring charge that you had to pay every month over and over and over again. And the bandwidth with the advent of streaming audio and streaming video, the T1 lines, 1.54 megabit, that was getting a little slow. If I want to do circuit switched, I've got the option of the dial-up. So we can use an analog type haze type modem, convert the digital ones and zeros into the screeching cats modem noise that we can go over an audio telephone line. So we're limited to about 50 kilobit per second. That's pretty slow. That's about 5,000 characters per second. It would take a long time to download a big file. ISDN was a little faster. It was 128 megabit, and it worked. The big thing is it worked over the existing copper wires that have been there for 100 years. You didn't need to run a new type of shielded copper cable or fiber optic cable. And the phone company understood this, and you were able to order an ISDN cable, and we didn't have the problems we did with when DSL came out. You had to be within like 2 miles of the telephone company central office. ISDN works over very long distances, so you could get it out in the country in Blum or something like this. Frame relay is fairly much legacy now in the United States because we have so much Ethernet handoff stuff, but it's still used in many parts of the world, like, for example, South America. It's just like Ethernet, except it runs over telephone lines. It's non-broadcast multi-access. So Ethernet is broadcast multi-access. If I send a broadcast, everybody hears it. Frame relay is non-broadcast multi-access, but for example, the home office in Orlando had a frame relay line that went to all the branch offices throughout the world. And if we needed a broadcast function like RIP broadcasts, its routing table, we could artificially recreate that with the broadcast keyword. So frame relay creates a permanent virtual connection, and we use data link connection identifiers, or DLCs. Think of this as equivalent to the MAC address. In an Ethernet network, the MAC address identifies your wire. In a frame relay circuit, the data link connection identifier locates your wire that goes to your branch office. Asynchronous transfer mode used fiber optic cables, and it was instead of frames like Ethernet and frame relay, used frames that are 1,000, 1,500 characters in length. Asynchronous transfer mode only used something called cells. It was 48 bytes of data and an extra 5 bytes for overhead. But it was very fast. It was excellent for streaming audio and streaming video because the little cells would go much faster than one huge frame. It was the darling technology of the early 1990s, and a bunch of big companies adopted it because it was very, very expensive. ATM's lunch got eaten by fast Ethernet and gigabit Ethernet. It was a much faster technology. It was easy to understand. The engineers already understood standard Ethernet. So asynchronous transfer mode became sort of a niche technology. So today, you're probably not going to use a dial-up modem. You're probably not going to use a T1 line. You're probably not going to use frame relay. You're probably going to use some type of Ethernet handoff technology. And a good solution would be, we have to connect our offices to the internet anyway. Internet connectivity is available throughout most of the world, some method, wireless, wired, fiber. So this gives us this connection that everybody needs to the internet, and let's just run all our traffic over the internet, and we'll encrypt it if we need to. So these days, we would normally use a dedicated connection. We would go to, I've heard a figure that says that 90% of the fiber optic cable that's buried in the United States today is dark fiber, and no one is using it. So it's going to be real easy to find a piece of fiber optic cable between two locations that you have and light it up with your own laser light and connect branch offices together with. Packet switched, Ethernet wide area network services like Southwestern Bell wide area network. I think they called it GigaMan. If you ordered it from the phone company AT&T, you asked for GigaMan service, and that was an Ethernet carrier, Metropolitan Ethernet carrier type services you could get. And we had our campuses. I think we still have our campuses connect together with that 10 megabit, fairly fast Ethernet service back and forth. Multi-protocol label service, MPLS. It's like frame relay on steroids. It uses a label service, and the carrier will set up a virtual circuit back and forth between your offices. And you may be sharing some of the wires with other customers. They really can't hear your stuff, but if you're concerned, you can always set up a VPN and you can encrypt it to make sure that nobody can hear it. But today, a very popular standard is just wherever you are, you get an internet connection. You know, using cellular, municipal Wi-Fi, even a satellite or WiMAX connection. You can get some connection through a cable or DSL modem, typically to an internet service provider, and then everybody else, all the other offices of the company, can connect with you in that fashion. So Ethernet, wide area network service, Metropolitan Ethernet, Ethernet over multi-protocol label service. There are several different technologies that you can use here. And in most heavily settled, thickly settled areas like cities, there's already plenty of fiber optic on the ground, and you can get this type of service. Now, if you go to the west end of Galveston Island, where there's nothing but mosquitoes and rattlesnakes, you can't get fiber optic service. Or if you go to, somewhere between Whitney and Cleburne, like the little town of Blum, you probably can't get fiber optic service. But in most big towns and big cities, you'll be able to get this service. The phone company or some service provider will offer it. So the old traditional serial point-to-point T1 links are slowly dying out, and they're being replaced by very fast Metropolitan Ethernet links, which if you had your choice of 1.5 megabit or 10 gigabit, which one would you want? So multi-protocol label switching is a way we can connect. We can go to a carrier, and it doesn't matter where the individual home workers or the individual offices are located. They could be using DSL or cable or Metropolitan Ethernet. We can go to a carrier, and this carrier will apply labels to our packets, identifying it as belonging to our company. And when it gets to the individual user or the office full of users at the remote location, they'll hear the stuff just like if they were directly attached to the home office with a private T1 line, but much more quickly. And it supports some things we need today, like quality of service so that the phone connection can be promoted to the head of the line. We can do virtual private networks if we're having data that we don't want our competitors to get a hold of, and things of that nature. Okay, wired and wireless. We can use twisted pair copper cables. We can use fiber optic cable. This gives us some reliable, consistent bandwidth, fairly low error rates. So DSL, cable modems, optical fiber networks are all examples of this. In the Wi-Fi world, we can use, in the wireless world, some cities have municipal Wi-Fi. You can use cellular. If you're in the middle of the desert in Arizona and there's no wires nearby, you can use satellite internet like Hughes network. Back at the west side of Galveston Island, they've not run any cables there because it's not that many people. It's not profitable to the company, so they don't do it. But you can set up a WiMAX tower and then broadcast that. WiMAX is kind of like Wi-Fi on steroids. It goes more than 300 to 600 feet. So the people that have these beach houses on the west side of the island can still get their internet service, even though they're too far away to get it from the phone company or a cable company. Okay, the old traditional DSL was a system that, if you look at this graph, the left part of the graph is the audio frequencies that you can hear. Telephones are about 3,500, 4,000 hertz of bandwidth. That's not hi-fi. It's not CD quality. It's not FM quality. It's not even AM quality. It's a little bit worse than that. But it's enough that I can hear what you're saying and understand what you're saying, and I can recognize it's you. I can recognize the caller. The higher frequencies are not used. So the engineers figured out that they could put some data in those higher frequencies They already proved this with T1 lines since the 1950s. And that the analog telephone conversation in the green part can carry on at the same time that you can do digital data in the ADSL part. Asynchronous DSL means that the download rate is much faster than the upload rate. This is perfect for residential home customers because they want to be able to download fast, and they only need to send up an occasional D for download command upstream. So it's perfect for home users. Business users want symmetrical DSL because they want to put service in their business. So symmetrical DSL, it's not $50 a month. It's much more expensive. It has a higher capability, has higher technical standards. This is going to vary according to how far away you are from the telephone company's central office. So if you get over DSL, you can't get over about 2-3 miles. It kind of peters out. You can't use it. So DSL connections, I've got a home router in my house. I've got a DSL modem. Actually, the phone company gave me a combination home router and DSL modem all in one box. It's got Wi-Fi in it. And then the telephone line runs back through, it could go back to the central office. In Arlington and some other areas where they have new housing development take place. About 20 years ago, Southwestern Bell had a thing called Project Pronto, and they put little pedestals out in the new neighborhoods. And they ran fiber optic cable to the pedestals, and then they ran traditional wires to the homes. So my DSL connection is to a little pedestal that's very close to my home. And then it has a fiber optic connection that goes back to the real central office. So that digital DSL access multiplexer, the DSLAM, has to be within 18,000 feet of the subscriber. And it's within a couple thousand feet of my house. And then the fiber optic cable goes back to the telephone company, and they split out the voice conversations and send it to their dial-up phone network, and they split out the data connections and they send that to the internet. So ISPs use point-to-point protocol. The old traditional DSL modems use this. So when I configured my home router, I would configure it with my name and my password that I've been assigned by the phone company. And point-to-point protocol has a mechanism where you can enforce passwords. So remember when I told you point-to-point protocol was used for America Online? The subscriber would dial in, they would check his name and password. If his bill was paid and up to date, he would get onto the America Online connection. If he wasn't, he would be denied the connection. So point-to-point protocol is used to authenticate the subscriber with his name and password, and it's kind of like a mini DHCP. It'll assign an IP address to him. And it has some management features that keeps track about errors on the line and makes sure that the connection is maintained high enough quality. So point-to-point protocol over Ethernet is done. I did it with the router part. My home router had the router point-to-point protocol over Ethernet client in it. I put my name and password in the router. And then I could attach as many home devices as I wanted to the Wi-Fi or to the Ethernet connection on the router, and I would get a connection. If you were a salesman with a single laptop, you might put the software on the laptop itself and do that. Cable technology is actually very similar in architecture to DSL technology. The cable modem carries all the television signals, and then he uses a couple of the television channels bandwidth to do internet connection as well. And then when it gets back to the cable company head end, they have a cable modem termination system that splits out the TV channels that goes to their satellites, their TV satellites, and then it splits out the internet signals and it goes to some high-speed internet connection they have to the internet. Some communities have optical fiber to the users. Sometimes it's through a municipality. Sometimes it's through a for-profit company. So fiber to the home, that means the fiber actually comes to your house and it goes in that little gray box on the back of your house. They cut the copper. Fiber to the building, it comes to maybe your apartment building, and then copper cables will be run to each of the individual apartments in that apartment complex. A fiber to the node or neighborhood, it comes to a pedestal box somewhere within a few blocks of your home, and then twisted pair copper cable or coaxial cable goes to that. That's how I'm getting my internet service from the phone company. They have a fiber cable that comes to a pedestal within a few blocks, and then I have the twisted pair that comes to my house, and I'm limited to about 75 megabit. They're digging and putting fiber in the neighborhood, and if I get the fiber connection, I'll get the whole gigabit connection because it'll be fiber to the home at that point. Okay, municipal Wi-Fi. Some cities offer this. Oh, the corporate people hate this. They don't like to compete with the municipalities. They call it an uneven, unlevel playing field because it lowers their profits. Because the municipalities have the advantage of, well, we have a lot of water pipes and sewer pipes. We can run the fiber through those. We don't have to dig and put them in there. And we don't have to make a profit. So the corporations have been pretty successful on a state-by-state basis by going to the state legislatures and trying to block municipal Wi-Fi. A couple of states are doing it pretty good. Tennessee's doing it pretty well. When they had Hurricane Katrina in New Orleans, a bunch of volunteers set up free networks using municipal Wi-Fi so that people could, get onto a Wi-Fi network and tell their people they were safe. And they got the Louisiana state legislature to shut it down because the cable companies and the phone companies don't want to compete. Well, how can you compete with free? Another technology is cellular. So all the cellular companies are offering internet-based access. You can we're going to give the students, the board bought 4,000 Chromebooks, and they're being distributed, they're going to be distributed to students that don't have their own home internet technology or have a device. And they're going to give them a hotspot, a cellular hotspot, so that they can communicate with the internet. Maybe they don't have internet connectivity at their home. Satellite internet, like Hughes, is a system that uses the same type of dish. If you have Dish TV or Direct TV, it's the same technology. The satellite points to a point up in the sky where they have their stationary satellites, and you can get internet access in that fashion. It is subject to, if there's rainfall, it can make it fade. WiMAX is a standard that's Wi-Fi on steroids, where you can set up, if you're a small business entrepreneur and you go to someplace in the country where they don't get internet access, you can set up a WiMAX tower and shoot out 10 or 20 miles to all the neighborhoods in that area and offer those people internet access so they couldn't get it before. Okay, I want to connect all my company offices together with the internet because the internet's pretty much available everywhere. But I'm sending secret marketing plans or revenue data, and I don't want other people to see it. It's not any of their business. So let's just encrypt this data. So VPN technology is a technology that allows us to use any type of internet connectivity we can get hold of and simply use encryption keys and encrypt the data. And only our offices or our employees working at home will have the proper encryption keys that will be able to decrypt the data and encrypt the data. So the two types is site-to-site VPN. The router at the Orlando office and the router at the Fort Worth office will talk back to each other over the standard internet connection. And those two routers will have the VPN code in them to encrypt and decrypt the data. The client machines in the Fort Worth office don't have to have any special software. It's in the clear to them over their Ethernet connection. If you're a remote access user at home, work from home, WFH, or you're a salesman at a convention, you can have the software on your laptop that will do the VPN encryption and decryption code, so you can use it anywhere. You can get Wi-Fi access in a coffee shop or something like this. And you guys probably already heard about you can get a VPN, so that if you're in a Starbucks and you're sending data and you don't want somebody to, splat ransomware on your PC or see what your data is, you can get VPN access, even for free. Some companies offer it totally for free. Like Kaspersky, the Russians. Hey, isn't it ironic? The Russians are giving us free VPN. Okay, we talked about single-homed and multi-homed and dual-homed. We can run a single connection to a single ISP, but if that ISP connection gets chopped up, we're out of luck. I can connect to the same ISP using two links, which if one wire gets chopped up, I still have some connectivity, but if the ISP has an outage, I'm out of luck. So multi-home, I'll run one wire to Verizon and one wire to AT&T. And that way, what are the chances of both these systems going down at the same time? At least I have some connectivity. And then dual multi-homed is the most costly, but it's the most redundancy. So many companies have a policy of business continuity of business operations, fault tolerance. we don't want to go down for any reason, because like, think of Amazon. If they lose a connection, they're losing people buying books, buying things. So let's look at comparison here. Cable is available many locations. It's shared by many users. Upstream data rates are slow if it's oversubscribed, if they have too many customers. Now they claim they can open up a couple more TV channels, bandwidth, and cure that dynamically if they want to. DSL is also asymmetrical, and that the download is real fast and the upload is about 10 times slower, but that's usually not a problem for home users because they're just browsing on the internet. Fiber to the home does require fiber to be pulled directly to your home, and it is available in some areas. It seems to be appearing mostly in the upscale neighborhoods, and they're kind of ignoring the neighborhoods where the socioeconomic numbers are lower, and they're not going to make a big profit off of those. Cellular mobile, if you have Wi-Fi coverage, you can use this. Municipal Wi-Fi, most cities don't have municipal Wi-Fi. The companies have been pretty successful in blocking this. In a few states, they're more successful. And if you're just in an area where there's no availability whatsoever, not even a Wi-Fi point, you can go with Hughes satellite to satellite type options. It's more expensive, it's slow, has a lot of latency, but it works if you need some type of connectivity. It's better than dial-up. Okay, we're not going to do this. And what I'm going to do now is stop this and go to A. And let's look at some of these virtual private networking concepts. So we're going to look at virtual private networking technology, how it works, encryption techniques, and look at something called IPsec, which means IP security, how this is used to secure our network traffic. So we already talked about office to office, site to site, and site to individual worker. We have to have special software in that laptop for this to work. But all the traffic, once it's on the public internet, it's already encrypted. I can see anything on the internet I want to. I can run Wireshark and see it. If it's encrypted, I don't have the key. I won't be able to tell what it is. So if I'm a spy for the corporate opposition, I won't be able to see it. So virtual private networking technology supports some types of encryptions. For example, when you go to your website, you go to your web browser, and you go to your bank and you transfer money back and forth, or you go to Amazon and you give your credit card number, you don't want everybody in the world to see that. So we use HTTPS, secure socket layer or transport layer security, that encrypts all that traffic so nobody can steal your credit card number. IPsec would be used for point-to-point VPN between a home office and a branch office. So this way we can save money because we'll just have one fast connection to the internet instead of a combination of a public internet and a private circuit. It gives us security because we can use encryption, and we can make sure with your name and your password that you're authorized to get to this stuff. We can add new users and just speed up our internet connection if we need additional features. A lot of companies are facing this now with work from home. And it's very compatible with pretty much any technology we got out there. So site to site. Site to site goes from a VPN gateway, a router at the home office will have do the encryption of the data. All the data within the skyscraper is unencrypted. Once it leaves the home office building over the public internet connection, it's encrypted with a key that no one knows except people in the company. The VPN router at the branch office location will unencrypt it. Some cable companies offer this VPN service. They'd like to charge more for it because you're doing business instead of just residential use at home. So some home routers have a VPN feature in them where you can do this. Otherwise, you've got to install it on the device itself. So the businessman's laptop computer has got the have to have the Cisco or other kind of VPN software on it to be able to dial in. This is the type of connectivity that the college has made available to employees and teachers at home if they need them, if they want to dial into the college network and see our private 10.144 network. We can VPN to it and do that stuff. So enterprise VPNs are used to connect from a site-to-site and remote-based employees. Service provider VPNs are used by the service provider. They will do this stuff for us, and they'll use something like multi-protocol label switching to make sure our traffic is segregated from other people's traffic, so that they can't hear our traffic, they can't see it. So a remote access VPN, users that are at a remote branch, or maybe they're working from a hotel room or working at home, they need to be able to connect to the company. So a client-based VPN connection, we're using a combination of Cisco software and Palo Alto software for Tarrant County College. I can connect to that. If I don't have the software on my PC, I can connect to a special web server at TCC and download the software and install and configure it on my laptop. And then I'll be able to connect to the TCC offices, but I have to have my name and password that's on the list of people that are authorized to do this before I would be able to make that connection. However, how about clientless? Well, many commercial line of business applications these days have been written to run from a web browser. I don't have to install the advantages. I don't have to install any specialized software on the computer. They can just run any regular web browser and connect to the company and see how many widgets is in the warehouse or how many days of vacation they have left. So if we want to secure that data, or if I go to my human resources site, I don't want other people to see my salary and my social security number. We can use secure web, HTTPS, which uses secure sockets layer or transport layer security, and it encrypts the data, and no one on the internet can see it because it'll be encrypted to them. So IPsec, it has good support for almost any application program you run on your PC, even if it cannot be web-based. Maybe the company is using an old legacy program that tells me what's in the warehouse, and it hasn't been rewritten yet to run in the web browser. I would have to use IPsec for this. IPsec has very strong encryption, very good encryption strength. It's fairly complex because it requires that I install a VPN client on the host machine or have the VPN client installed on the router that's the default gateway for that host machine, and it has more limited connectivity. However, web-based, like secure socket layer, the more modern version is called transport layer security, it is limited to only stuff that's been rewritten to work with a web server and a web browser. It does have authentication. You can use 256-bit keys. It's not complex. Any web browser will work. All modern web browsers support this. So the connectivity options are anything that I can connect to the internet with at all is going to be great. I can use this and just run my standard web browser. So on a site-to-site VPN, I'm going to run traffic over the internet. I'm going to use probably IPsec, IP security to encrypt the traffic. So in-host can send normal traffic through a gateway. To them, it's unencrypted. To the people in the office building, it's unencrypted traffic on their PC. To the work from home person with a laptop, it's unencrypted traffic coming in and out of his Wi-Fi or internet connection. Once it hits the VPN gateway, he will encrypt the traffic. And then he'll relay it to the home office, and the home office will remove the encryption, and it's an ordinary packet again when it hits the home office. So generic routing encapsulation is a non-secure VPN protocol. I don't want to have encryption security. I just need a connection. I can use this to encapsulate upper layer network layer protocols. GRE doesn't have encryption by itself, but if I need that, I can use VPN. I can use IPsec to do that if I want to. So a GRE packet can be encapsulated into an IPsec packet, and I could forward it securely and encrypt it if I needed to. We used this technique many years ago back when we were running Novell networks, which used IPX packets and SPX. IPX is like IP, SPX is like TCP. And the carriers are only providing IP packets. So we would encapsulate our Novell packets inside an IP packet, tunnel them, send them to the home office, and then the home office would open up the IP packet, bring out the Novell packet, and send it to the Novell server at that site. And sometimes these days they're using this for if you have a service provider that only supports IP version 4, maybe you can encapsulate an IP version 6 packet in an IP version 4 and send it over the carrier, and then it'll be turned back to IP version 6 back at the home office. So the header has to have a standard IP packet to go over the carriers. Pardon me. So this blue header at the beginning, that's a standard IP packet header, source address, destination address, things of that nature. And then the GRE has its own header, and he encapsulates the IP packet that has the secret data in it, or maybe the IPXLL packet or the IP version 6 packet. That's what's being transported through the standard IP. And this way, any carrier will be able to support IP version 4, and we'll be able to hear this data back and forth. Now, if we use IPsec, we want to be able to exchange, in this example, the OSPF routers want to be able to exchange their hello packets and their path updates with each other. So the OSPF packets is our passenger protocol, sounds like passenger pigeon, and that would be encapsulated in GRE, the carrier protocol, the carrier pigeon, and subsequently it would be encapsulated in the tunnel. Now, GRE gives you some options of either encapsulation or authentication. You can use whatever you need in here. It's like Chinese restaurant. Choose one from column A and one from column B. Dynamic multi-point VPNs, if we have a lot of sites, many companies have, when I was in Harcourt, we had 100 offices throughout the world. We were on every continent except Antarctica. So Cisco offers, this is Cisco marketing buzz right here, okay? Cisco offers this multi-point VPN service that you can build multiple VPNs. And then you can create VPNs for security between the sites that you need to do. IPsec virtual tunnel interface is a method for, again, providing an easier method for configuration and send IP unicast, IP multicast, encrypt the traffic, and it works in either side-to-side or hub and spoke technology. The service providers that have multi-protocol label service, which is what I call frame relay on steroids, it's replaced the old frame relay Delcies with multi-protocol label service labels, where they label Acme Corporation, all the packets are labeled with that packet number. It's a number, not a name. And then it's routed through virtual private circuits, virtual private dedicated circuits to their branch offices. And in theory, no other company should be able to hear this data. But if you're concerned, you can encrypt it and add an extra layer of security. So at layer 3, you would run OSPF or BGP, Border Gateway Protocol, on your company routers, and you would peer up with the service providers routers. And layer 2, it's like a complete data link layer. It's like almost like an Ethernet connection between the branch offices. So the router at the Orlando office would send hello packets back and forth to the router in the Fort Worth office, and they would have no knowledge of the service provider's carrier. So these are our two options. Choose either layer 2 or layer 3. Now let's look at IPsec and look at some of the protocols that are in there. No video, I can't transmit video here. You can see this video at home. If I tried to transmit this video right now, you would not hear the audio. You would just see the picture. Okay, so IPsec is a standard, an Internet Engineering Task Force standard. And this defines how VPNs can work. So here's some of the things that VPNs give us. We can have confidentiality. We can encrypt the data with keys so that nobody else can see the contents. We can have integrity. Think of the frame check sequence at the end of an Ethernet frame that checks to make sure that the Ethernet frame has not been altered or corrupted in any fashion. Because if it had been, the frame check sequence wouldn't match anymore, and it would drop the data. So integrity in IPsec is a way that you can make sure that, for example, when you download a installation file for a software product and they'll give you a hash code, you can check and make sure no bad guy has planted a virus into it. Origin authentication, non-repudiation. We can use a digital signature thing to make sure that when Microsoft sends something out, you can check to make sure it has Microsoft's key and it's not from you know, the Recrain or something like this. And then Diffie-Hellman, which we in the South call Dixie-Hellman. This is a way of doing key exchange because of the problem that symmetric keys are very fast, but they're difficult to exchange with each other. Asymmetric keys are very slow. So the Diffie-Hellman is a method for using asymmetric key exchange to exchange a very short session where we merely exchange a shared secret key, and then we'll switch to the shared secret key and get very fast processing time. Okay, here's the Chinese restaurant. Choose one from column A, one from column B. So we can use whatever type of, in IPsec, we can only use authentication headers to prove it came from the same place. We can encrypt the data with ESP, or we can use a combination of both. For confidentiality, we can use, you know, DES, triple DES, AES, SEAL, many different lanes of encryption is available. We can use MD5 hash or SHA hash. When you type enable secret class and then you do a show run, it doesn't say enable secret class. It says enable secret, the number 5, and then some garbage characters. The number 5 indicates that the password we use, class, has been hashed with the MD5 algorithm, and that's the MD5 hash of it. When you log into the Microsoft computer in the classroom, he hashes your password. We don't send your password over the wire. The server knows what your password is. He does the exact same hashing, and he compares his hash with the one you sent. If the one you sent matches, you must have typed the correct password. Then we can use authentication to make sure that you're the guy you say you are. And then we can use Diffie-Hellman to do key exchange, to do that momentary private key exchange, and then switch over to the shared secret key for faster processing time. Okay, choosing, first of all, we're going to choose the encapsulation type. Choose the protocol encapsulation type. We can either choose authentication header. There's no encryption. It's just you prove who you are. Or we can do encapsulation security protocol where we actually encrypt the data. Or we can do both. So authentication header is okay if I don't need confidentiality. If I use ESP, then I can also add the authentication. So confidentiality, when we talked about security earlier, in a previous class we talked about confidentiality, integrity, and availability. Confidentiality is maintained in a local area network with you putting in your name and password that's the proper password. And other people can't see your account information. It's in your shared folder. No one else can see it. So if I was going to transfer $100 from one account to another account, and I don't want the bad guy, can you tell who the bad guy is in this picture? We used to call them malicious users, so now they're called threat actors, because we don't want to make them feel bad about it. And he can't read the data because my account number has been encrypted. He can't see it. So the longer the number of encryption bits in the encryption key, the harder it is to decrypt in real time. And if we just use enough bits these days, 1,000, 2,000 bits, unless you're, the Russians or the North Koreans or something, you're probably not going to be able to break it in real time. So when Microsoft, I'm a Microsoft certified system engineer for Windows NT 4.0. I'm really dating myself. That's a 25-year-old technology from the late 90s. It used a 56-bit key. That's a joke. Today, that's a complete joke. You could break that in 10 seconds. But in the late 1990s, that was pretty good technology. Now, we had a NT 4.0 was 56-bit key, but if it was an export to Cuba or Russia, it was a 40-bit key because we didn't want to give them the more sophisticated encryption technology. Later on, they used triple DES, which was I encrypt it with 56 bits, then I encrypt it a second time, and then I encrypt it a third time. And then when I receive it, I decrypt it 1, 2, 3, and now I've got my original data back. AES has more number of bits. SEAL uses 160 bits. That's a good thing to use today because it has more bits that you can encrypt the data with. Now, integrity. I want to download a ISO file for a installation of Linux, and I want to make sure it doesn't have any viruses injected in it. So what the vendor of the Linux distribution can do is publish a hash, an MD5 of it, and publish it on his website. And then when I download the ISO file, I can scan the file and calculate my own hash, and it should match what he publishes on his website. I know now that some guy hasn't gone in the middle and inserted some bad code in it. The code matches perfectly. So this is to make sure that the data hasn't been messed up, much like the CRC code on Ethernet frames. So I can pre-share a key, but that doesn't scale up well. And how do I get the key to all the individual people? So the other alternative is digital certificates. So I can publish my digital certificate like my public key. You can publish your digital certificate like your public key. And then using each other's public keys, we could share secret information with each other. So Diffie-Hellman is a mechanism for exchanging a shared secret key over an insecure channel. So if I wanted to send the shared secret key to my, say I was in the CIA, and I want to send the shared secret key to my guy in Moscow. He works for the embassy. He's really a spy. So could I put the key on a flash drive and send it to him in an envelope? Well, heck no. The KGB is going to steam the envelope open, and he's going to get the key. So we need a method that we can get the key to him without people stealing it. So here's the problem. Asymmetric shared keys are very, very slow processing power. However, the key distribution problem has much better in that I can create a key pair. One's a private key, and I don't tell that to anybody. My public key I publish to the world plus dog. And I can send you my public key, and you can send me your public key, and I can encrypt something with your public key and send it to you, and only you will see it. And you can encrypt something with my public key and send it to me, and only I can see it. So this is the mechanism that Diffie-Hellman uses. We use this, we exchange our public keys with each other. Then we send this mechanism to send each other a shared secret key. And since it's encrypted, nobody else can see it. Then we're going to stop using the public-private key pair because it's too damn slow. And we're going to switch to the public key and use this. Sorry, no videos for you guys today. Hey, is that it? Okay, we finished. Okay, so good news, no labs this week. Thursday, I will cover Chapter Module 9, Quality of Service. And thanks for coming and meeting with me today, guys. And looking forward to meeting with you guys again Thursday. And this is Mark going mute.